What if you had a mental tool that could just slice through incredible complexity and reveal a simple, powerful truth? A way to predict how massive systems will behave just by looking at a few key details. Well, today, we're going to dive into one of the most elegant, most powerful problem-solving methods ever devised. Our story kicks off in 1945 with the Trinity atomic bomb test. Now, the amount of energy released by this terrifying new weapon, that was one of the most closely guarded state secrets in the entire world. The US government released a few photos, some film footage, but they kept all the crucial data under lock and key. Or so they thought. Because all the way across the Atlantic, a British physicist named G.I. Taylor took one look at these public domain images, scribbled down some calculations, and figured out the bomb's yield. And get this, his estimate was shockingly close to the top secret value. The question that just baffled everyone was, how? How did he do that? Well, to understand his genius, we first have to wrap our heads around a universal problem that this way of thinking completely solves.
And that brings us to a challenge that engineers and scientists face every single day. It's called the scale-up problem.
Okay, so imagine this. You've got something that works perfectly in the lab. A little chemical process, a model ship in a test tank. It's great. But how do you know, really know, it's going to work when you build the giant, multi-million-dollar factory or the full-sized ocean liner? A mistake at that scale isn't just a little error. It's a catastrophic disaster. You can't just cross your fingers and hope for the best. You need a set of rules, a kind of secret language that the universe itself speaks. And that secret language, the very foundation of G.I. Taylor's method, is called dimensional analysis. At its heart, the idea is beautiful in its simplicity. Any real law of physics has to work no matter what units you're using. The relationship between force, mass, and acceleration is the exact same whether you're using kilograms and meters or pounds and feet. The universe doesn't care if we use meters or miles, right? And this simple constraint, it's incredibly powerful. Let's see it in action. Okay, let's take a classic pendulum. What do you think determines its period? How long it takes to swing back and forth. You might guess the length of the string, the mass of the weight, and of course, gravity. So let's look at their fundamental dimensions. The period, well, that's a measure of time. The string's length is obviously length. The weight is mass. And gravity is an acceleration, which has dimensions of length per time squared. Now here's the puzzle. Combine those pieces to get a result that's only in units of time. If you try to stick mass in there, there's nothing else to cancel it out. It just doesn't work. The only combination that spits out a clean unit of time involves just the length and gravity. And this tells us something incredible, something you might not expect. The mass of the pendulum has absolutely no effect on its period. A simple rule of logic just revealed a physical law, and we didn't have to do a single experiment. Now, when you start applying this kind of thinking to more complex stuff, you get something extraordinary. Dimensionless numbers. Seriously, you can think of them as the universe's secret recipes. These special numbers boil a whole complicated physical situation down to a single value. They're basically a fingerprint for a process. And here's the magic part. If the dimensionless number for your tiny lab model is the same as for your giant real-world system, then you know their physical behavior will be similar. This is the absolute key to scaling things up reliably. And there are tons of these recipes, each for a different kind of situation. Let's just look at three famous ones. You've got the Reynolds number, which tells you if a fluid flow is going to be smooth and laminar or chaotic and turbulent, which is, pretty essential for designing a pipeline. Then there's the Froude number. That one is all about the waves a ship creates, so it's absolutely crucial for designing an efficient hull. And the Euler number helps engineers predict and manage pressure drops in all kinds of systems. This slide is a brilliant breakdown of how these recipes are made, using the Reynolds number as an example. See, it combines four things: the fluid's density, its velocity, a characteristic length like a pipe's diameter, and the fluid's viscosity. Each one of these has its own messy combination of mass, length, and time dimensions. But, and this is the cool part, when you arrange them in just the right way, in that specific recipe, bam, all those dimensions, the m's, the l's, the t's, they magically cancel each other out. And what you're left with is a pure, clean, dimensionless number. And that one number tells you the whole story of the flow. All right, so armed with this powerful way of thinking, let's go back. Let's go back to G.I. Taylor and that top secret explosion. Let's solve the mystery. So here's what Taylor did. He reasoned that the energy of the bomb, let's call it E, had to be related to the size of that fireball, its radius, r, at a certain time, t, after it went off. The only other major factor was the stuff it was expanding into, the air, which has a certain density, rho.
He then just looked at the fundamental dimensions of these things: energy, radius, time, and density. And just like with our pendulum puzzle, he realized there was only one possible way they could be combined to form a dimensionally consistent equation. That was it. And that one single equation allowed him to calculate the energy, E. It was that simple and that profound. Taylor's feat was absolutely spectacular, but this method isn't just for uncovering military secrets. It's for building our entire modern world. I mean, today this way of thinking is used literally everywhere. At the center of it all are those fundamental dimensions of mass, length, and time. And by understanding how these basic building blocks relate, engineers can do incredible things. They can make sure oil flows just right through thousands of miles of pipeline, design gigantic chemical reactors that work efficiently, and test a small, cheap model of a ship to perfect the design of the real, massive thing. This kind of thinking underpins so much of modern engineering. So, just how powerful is this really? Well, get this. For one classic problem, figuring out the pressure drop in a pipe, using dimensional analysis reduced the number of experiments you'd need to run from 625 down to just a handful. That is an enormous saving in time, money, and energy, all thanks to this one simple principle. So, okay, let's pull all of this together. What's the big idea here? What should we really take away from all this? You know, I think the physicist Lord Rowley really hit the nail on the head over a century ago. He said he was often amazed that people would conduct these huge, elaborate, expensive experiments to discover new laws that, as he put it, could have been predicted from the start after just a few minutes of thinking about it, using these exact same principles. Ultimately, it all boils down to this. Nature follows consistent rules, and by focusing on the fundamental dimensions of a problem, the basic units of mass, length, and time that describe it, you can cut through all the noise, reveal the underlying physics, and predict how a system is going to behave, whether it's the size of a teacup or the size of a skyscraper. And this leaves us with a final thought. This is so much more than just a tool for physicists and engineers. It's a really powerful way of thinking for all of us. So the next time you're facing some big, hairy, complex problem, try to stop and ask yourself, what are the truly essential variables here? What are their fundamental dimensions? You might just be surprised by the beautiful simplicity you uncover.